What if the very thing that makes our brains so uniquely powerful, so incredibly adaptable, so, well, fluid, is something that even the most advanced artificial intelligence is only just beginning to grasp? Imagine a computer that isn't just mind-bogglingly fast, but truly understands, adapts, and learns in ways current AI systems can't quite replicate, processing information with a dynamic elegance we're only just starting to unravel.
It's more than just a compelling thought. It's a fundamental distinction, really.
Hmm.
The core difference lies not simply in how quickly information is processed, but in the very architectural and computational principles at play. It's about moving beyond sheer speed to a deeper, more sophisticated kind of intelligence.
Yeah. That's a perfect way to put it. Welcome to the Deep Dive, your shortcut to understanding the most fascinating insights at the intersection of science and technology. Today, we're taking a profound plunge into the world where neuroscience directly informs our understanding of artificial intelligence. We're going to dissect the truly profound distinctions between the human brain, specifically its cerebral cortex, and the sophisticated AI systems we hear so much about today, particularly, deep neural networks.
Yeah, and our deep dive into this fascinating topic is heavily informed by the insightful work of neuroscientist Wolf Singer. He presents a truly compelling argument for the brain's unique computational prowess, highlighting how it leverages the temporal dimension, massive recurrence, and incredibly dynamic learning mechanisms in ways that, frankly, silicon-based AI has yet to fully capture or replicate. His work helps us understand the brain not just as a complex machine, but as an emergent living system. It's quite profound.
Our mission today is to uncover why the brain operates so fundamentally differently. We'll focus intently on its reliance on the temporal dimension, its masterful use of time, its massive, intricate web of internal connections, and those unique self-organizing learning mechanisms that make it such a powerful and flexible learner. By the end of this deep dive, you'll have a cutting-edge understanding of how brains compute and how that stands in stark contrast to the AI systems that, dominate our headlines.
Get ready for some genuine aha moments because this perspective truly shifts how you view intelligence. As we unpack the brain's secret sauce, its incredible ability to integrate time and dynamic relationships into the very fabric of information processing, you'll gain insight into just how profoundly different it is from the conventional, clocked, and often rigid computations that define most of modern AI. It's a journey into the very essence of natural intelligence and what makes your brain so extraordinary.
Okay, let's unpack this by first setting the stage, because Wolf Singer, a renowned neuroscientist, makes a really bold and provocative claim right out of the gate. He argues that natural systems, and specifically our cerebral cortex, utilize fundamentally different computational principles compared to artificial systems, like the deep neural networks that power so much of today's AI.
That's a crucial starting point. Singer's core premise is that while both types of systems aim to process information, the brain leverages the temporal dimension for its computations in a way that clocked artificial networks simply do not. He posits that the brain essentially functions more like an analog computer, where time itself isn't just a measure, but a critical, integral element in computation. Think about it. Traditional digital computers operate based on discrete steps, right? Driven by a master clock ticking billions of times per second. Every operation is precisely synchronized to that clock.
Right, step by step, perfectly timed.
Exactly. The brain, on the other hand, seems to be continuously flowing, adapting, and processing information in a fluid, real-time continuum. And in this system, the precise timing of events carries as much, if not more, meaning than just the presence or absence of a signal, like a simple 1 or 0.
That's a huge distinction, and it already paints a picture of a system far more dynamic than a traditional computer. So it's not just about what information is processed, but how it's processed within the flow of time itself. And a big part of that how comes down to something Singer calls massive recurrence. When we talk about the brain's wiring diagram, we're not just looking at signals moving from one point to the next in a straight feed-forward line, like data flowing through a pipeline.
Absolutely not. Massive recurrence in the cerebral cortex refers to the extensive, dense, and intricate connections that exist within and between nearly all layers of neurons. This isn't just an architectural feature. It's a fundamental organizational principle that underpins how the brain functions. Unlike many deep neural networks, which are predominantly characterized by more straightforward, hierarchical feed-forward processing, where information largely flows in one direction, input layers to hidden layers, then output layers, the brain has this unbelievably intricate web of looping reciprocal connections.
So it's not just a one-way street or even a highway with a few exits. It sounds more like a sprawling, multi-level city with roads, tunnels, and bridges connecting every district to every other district, allowing for constant feedback, crosstalk, and reevaluation. Data isn't just moving forward, it's reverberating.
That's an excellent analogy.
Hmm.
Singer points out that the canonical circuit of the cerebral cortex isn't merely feed-forward. It's defined by prominent tangential action collaterals. These are pathways that create robust reciprocal coupling among neurons. This means neurons aren't just sending signals to the next layer in a processing chain. They're simultaneously looping back, communicating intensely with other neurons in the same layer, and even sending signals back to previous layers. And the sheer scale of this is staggering. Approximately 80% of the adaptive contacts in the cortex, the points where neurons actually influence each other, are due to these recurrent connections.
80%, aha.
That number itself, 80%, unequivocally highlights how central this architecture is to the brain's computational strategy. It's not a mere embellishment, it's the very foundation.
80%. That's genuinely mind-boggling when you think about how different that is from what we typically build in AI. And it's not just a static wiring diagram either, is it? It's constantly in motion.
Not at all. Not even close. This intricate looping connectivity gives rise to incredibly complex, high-dimensional, nonlinear dynamics. Think of it not just as computing, but as simulating possibilities in real time. This dynamic interplay allows the brain to anticipate, to imagine, to truly understand context and relationships in a way a purely feed-forward network, which is primarily designed to process fixed patterns, simply cannot. These dynamics aren't just a byproduct. They are actively exploited as the brain's primary computational strategies. This represents a profound divergence from the more linear, often feed-forward processing that characterizes much of artificial intelligence today.
So it's not just about the physical structure, but what that structure enables in terms of dynamic behavior. And a crucial part of that enabled behavior is how the brain learns and adapts, which brings us to self-organization and adaptive synapses. Current AI systems are largely designed and then trained. How does the brain approach this?
Indeed. Natural systems are fundamentally distinguished by learning mechanisms that facilitate extensive self-organization. This is a game changer. It allows them to perform complex computations that are often exceptionally challenging, if not impossible, for conventional artificial systems, especially those relying on fixed architectures. The neurons in natural systems aren't just passively waiting for instructions or pre-programmed rules. They possess adaptive synapses that continuously adjust their strength and efficacy based on very precise temporal correlations in neural activity. This isn't just about a fixed architecture that gets tweaked during training. It's a continuously adapting, self-modifying, self-optimizing network that learns and reconfigures itself throughout its entire existence.
That's fascinating. It sounds like the brain is constantly rewiring itself based on its experiences, particularly focusing on when things happen in relation to each other, like a gardener constantly pruning and growing new branches based on what yields fruit.
That's a very apt analogy. The precise timing of activity between neurons dictates how their connections change. If two neurons consistently fire together, their connection strengthens, making them more likely to fire together in the future. If they fire asynchronously, their connection might weaken. This continuous dynamic adaptation is absolutely fundamental to how the brain learns, adapts to novelty, and processes information. Think about learning a new skill like riding a bicycle or playing an instrument.
Right.
You don't just download a static map. Your brain is constantly, subtly rewiring itself with every practice session, every new movement you attempt. This isn't a fixed program. It's a living, breathing, self-optimizing network. This ability for continuous, unsupervised self-organization is a monumental challenge for AI. Imagine an AI system that could truly learn simply by observing the world, constantly refining its own architecture, without a human programmer explicitly telling it what to do. It's about becoming, not just being programmed.
That makes so much sense because our world is so dynamic, so fluid, and our learning needs to keep pace. Okay, let's delve into a core cognitive challenge. How do our brains actually represent and classify the immense diversity of objects around us from a seemingly limited set of elementary features? It's really all about encoding the relations between components. How do we see a cup not just as a random collection of lines and curves, but as a single coherent object with a specific function? Wolfsinger outlines two primary strategies for encoding these relations, and one of them is very familiar to modern AI.
This is a truly critical challenge for any cognitive system because the world is infinitely complex. But our brains don't possess a unique pre-wired detector for every single possible combination of features. Singer's first strategy is what he terms convergent feed-forward circuits. And as you mentioned, this is indeed the foundational principle behind many artificial deep learning networks.
The AI way, if you will, or at least one of its main roads.
Exactly. In this approach, neurons tune to specific elementary features, say a short vertical line, a curved edge, or a specific color, converge onto higher layer nodes. These higher layer nodes then become exquisitely specialized to respond to specific conjunctions of those features. So you might have a neuron in a deeper layer that fires only when it detects a vertical line and a horizontal line in a certain configuration forming, say, a corner. As you move up the hierarchy, these neurons become increasingly selective, responding to more complex conjunctions, eventually forming representations of entire objects like a face or a chair.
And this is precisely how many deep learning networks are structured, right? They have layers of artificial neurons that build increasingly complex representations, from simple edges to geometric shapes and then to entire objects or concepts. Each layer essentially combines the features from the layer below.
Precisely. It's a very intuitive, powerful, and successful method common to both natural visual systems and artificial deep learning. However, it runs into a significant problem that Singer terms the combinatorial explosion. Imagine trying to create a dedicated neuron or node for every single possible combination of features that exists in the world. How many unique combinations of simple lines, curves, and colors make up everything you might encounter, from a specific person's face to a unique type of tree swaying in the wind?
Oh, wow. That would require an astronomical, practically infinite number of nodes. Your brain would have to be impossibly massive to contain all those dedicated detectors.
It becomes computationally overwhelming and extremely costly in terms of biological hardware, demanding an almost infinite number of neurons. Furthermore, this method is inherently less adept at handling relations between temporally segregated events because it fundamentally lacks a built-in short-term memory of how things unfold over time. It's primarily designed for recognizing static, fixed patterns or spatial arrangements, not dynamic sequences.
So, if you needed to recognize a precise sequence of events, say, the specific hand gestures that form a sign language word or a specific melody played note by note, a purely feed-forward system would likely struggle without explicit and hardware-heavy mechanisms to remember each step in that sequence. This brings us to Singer's second strategy, which he highlights as the brain's truly clever and vastly more efficient solution: cooperating assemblies.
This is where the brain truly shines, particularly in the most evolved parts of the vertebrae, including crucial areas like the hippocampus and, of course, the cerebral cortex. Instead of relying on a dedicated pre-wired detector for every conceivable combination of features, this strategy involves the temporary, flexible formation of assemblies of neurons that collectively respond to related features. These assemblies are not fixed, they are dynamic, forming and disbanding as needed.
So it's not a permanently assigned neuron for cup, but a dynamic group of neurons that come together momentarily to represent cup and then can reconfigure for something else. It's a fascinating concept, a temporary assembly. But how does the brain decide which neurons join this assembly for cup at any given moment, and what stops it from, forming a cup chair assembly if a cup is next to a chair, if it's all about co-occurrence?
That's the essence of the genius and also the challenge, and it heavily relies on the brain's massive recurrent networks. Neurons coding for features that frequently co-occur in the environment, like the visual features of a cup, its handle, its specific color, its roundness, strengthen the reciprocal connections. And this is where we bring in a classic foundational principle of neuroscience: Hebbian learning. The famous adage perfectly encapsulates it. Neurons that often fire together eventually wire together.
Ah, the famous Hebbian rule. It seems so intuitive, but the implications are profound, aren't they?
They truly are. This principle explains how the adaptive horizontal connections within the cortex are dynamically shaped by experience. If two neurons, say one representing roundness and another representing handle, frequently activate at approximately the same time when you encounter a cup, their synaptic connections strengthen. This increased coupling makes them more likely to fire together again in the future, thereby forming a temporary, cohesive assembly that collectively represents the combined features, in this case, the object cup. This is not about a single neuron detecting cup. It's about a dynamic coalition of neurons representing cup.
And this sounds vastly more economical than the combinatorial explosion problem we discussed earlier. It feels like a much more elegant solution.
It is exponentially more economical in terms of biological hardware. Individual nodes, or neurons, are not permanently dedicated to one specific complex object or concept. Instead, they can be flexibly recombined into an almost unimaginably huge number of different assemblies, forming a true combinatorial code. This means a single roundness neuron, for instance, isn't permanently dedicated to just cups. It can be part of an assembly for cup, or for wheel, or for moon, or even for abstract concepts, depending on which other neurons it's currently collaborating with in a given context. That's an unparalleled level of flexibility and efficiency.
So the same round neuron could be part of an assembly for cup or for wheel or for moon, depending on which other neurons it's currently collaborating with, and the precise timing of their activation. That's incredibly flexible, like a small cast of actors who can perform an infinite number of plays just by changing their roles and interactions.
Exactly. Moreover, this strategy is exceptionally well suited for handling temporal sequences. The recurrent networks create a kind of fading memory through reverberating activity. This means that when a stimulus activates an assembly, the activity doesn't just disappear instantly. It reverberates within the network for a short period, a neural echo, if you will. This allows for the integration of temporally segregated information, making sense of sequences like words in a sentence or notes in a melody. It also enables powerful capabilities like pattern completion, recognizing a whole even from partial or noisy input, and the spontaneous generation of novel associations based on past experience.
That's really powerful. It's like the network has a built-in echo chamber that allows it to hold on to information for just long enough to connect it with subsequent information, creating a coherent narrative from a stream of sensory input.
However, this incredible flexibility and efficiency come with their own set of significant challenges. One of the major ones is maintaining network stability. You need incredibly sophisticated mechanisms to prevent runaway excitation, where the activity just spirals out of control into epileptic-like seizures, or, conversely, activity collapse, where everything just shuts down. This delicate balance is often achieved through intricate normalization processes and complex inhibitory interactions within the network. The brain has to carefully balance excitement and inhibition, like a conductor expertly managing the volume and tempo of a massive orchestra to keep these dynamic assemblies working optimally without chaos or silence.
So the brain's clever solution isn't just clever, it's also incredibly intricate and requires constant, dynamic, real-time control to stay functional. This brings us to another critical challenge the brain faces, often called the superposition catastrophe, or, more commonly, the binding problem. This sounds like something out of the science fiction novel.
It sounds dramatic, but it's a very real and core challenge for brain function. Imagine you're looking at two overlapping objects simultaneously, say a red square and a blue circle. Your brain has neurons that respond to the color red, other neurons that respond to blue, neurons tuned to square shapes, and neurons for circle shapes. The binding problem is, how does the brain know that this particular red belongs to that specific square and this particular blue belongs to that specific circle, especially if the objects are close together or even share some features? If all differentiation relied solely on increasing neuronal activity, just how much a neuron fires, it would be incredibly difficult to distinguish which features belong to which object when multiple assemblies are active at the same time. The features would just kind of superimpose, creating a perceptual jumble.
Right, it would be a jumble. You'd see red and square and blue and circle, but you wouldn't necessarily know that the red is the square or that the blue is the circle. It would be a chaotic soup of features. So how does the brain untangle this superposition catastrophe? How does it assign features to the correct objects?
This is where the critical proposed solution of multiplexing comes in, and it's truly revolutionary in its elegance. Instead of differentiating assemblies solely by which neurons are active, which is essentially what a rate code does, the brain achieves this by segregating these neural assemblies in time. It's a genius move to utilize the temporal dimension.
In time. So it's not just about what neurons fire, but when they fire, and perhaps even in what rhythm they fire.
Precisely. This temporal segregation is achieved through the precise synchronization of neuronal action potentials. Instead of simply increasing the firing rate of neurons belonging to an assembly, the brain has found a way to make those neurons fire in precise sync with each other. This becomes a kind of temporal signature for belonging together. Think of it like different sections of an orchestra. Each section is playing, but when they need to convey a unified melody, they play their notes in perfect rhythm and harmony.
That's a truly beautiful solution. So The neurons representing the red square might fire in one very specific synchronized rhythm, and the neurons representing the blue circle might fire in a slightly different but also highly synchronized rhythm. Even if both sets of neurons are firing at roughly the same overall rate, the timing becomes the differentiator.
You're absolutely on the right track. This leads us directly to the power of oscillations and synchrony in the brain. It's a fundamental property of neuronal networks to engage in oscillatory activity, meaning their electrical activity rises and falls in rhythmic patterns across an astonishingly broad range of frequencies, from very slow oscillations below zero point 0.1 hertz all the way up to incredibly fast ones, often exceeding 200 hertz, known as gamma oscillations. These oscillations are not just random noise, they are evolutionarily conserved across species, suggesting their fundamental importance in nerve cell and circuit dynamics, acting as a kind of internal clock for different brain processes.
So our brains are literally humming with different rhythms, different internal beats all the time. It's not silent up there.
Exactly. And these oscillatory patterns aren't just background noise. They serve a crucial computational function. They create periodic changes in excitability within the network, meaning neurons become more or less likely to fire at certain points in the cycle. This imposes a precise temporal structure on neuronal firing, which in turn facilitates precise yet variable temporal relations between interconnected network nodes. This phenomenon is sometimes described by the Arnold tongue regime, which in simpler terms refers to how neurons can lock into or be pulled along by a specific rhythm of inputs, creating stable, synchronized patterns even with varying stimulation. It's like a dancer finding the beat of the music and staying in step.
Okay, so the rhythm helps neuron to coordinate. And how does this rhythmic synchronized firing specifically help with the binding problem beyond just indicating relatedness?
Because of the brain's massive recurrent coupling, these oscillating circuits can naturally synchronize with each other. And here's the critical piece. Experience shapes the network such that neurons responding to features that often co-occur in the real world, like red and square when you repeatedly see red squares, become more strongly coupled. This stronger coupling makes them intrinsically more likely to synchronize their oscillations.
So the synchronization itself becomes the dynamic code for relatedness. It's the brain's way of saying, these pieces belong together right now.
Precisely. Synchronization serves as a general, flexible code for relatedness, effectively binding distributed neurons, perhaps spread across different brain regions, into a coherent, temporary assembly. This mechanism offers several profound benefits beyond just solving the binding problem. First, it's remarkably effective. Synchronization is as potent as simply increasing discharge rates and enhancing the efficiency of information transfer for downstream targets. A synchronized burst of activity gets noticed more easily by the next neuron in the chain. But the truly crucial advantage is that it allows for very short integration intervals for synchronous inputs.
Short integration intervals, meaning the brain can figure things out faster.
Yes, exactly. Downstream neurons can rapidly and unambiguously read out information from these precisely synchronized inputs. They don't have to wait for a lot of individual spikes to average out. They can detect a coherent, timed burst almost instantly.
And why is that rapid readout and multiplexing so important?
Because it enables much faster multiplexing of different assemblies compared to systems that rely solely on discharge rates. If you only had discharge rates, distinguishing between overlapping signals would require longer integration times to gather enough evidence, which slows everything down. With synchronization, the timing itself tells you which signals belong together, allowing the brain to rapidly switch its focus or process multiple streams of information in quick succession without mixing them up. This directly addresses the problem of slow readout and feature mixing inherent in purely rate-coded systems. It's like having different conversations happening simultaneously in a room, but each conversation has its own distinct rhythm, allowing your ear to pick out any one of them easily.
That's incredible. It's like the brain has its own built-in high-speed data transmission system where precise timing and rhythm are the keys to clarity and efficiency.
And it gets even more sophisticated. Simulations and theoretical work indicate that even subtle phase shifts within these delay-coupled recurrent oscillator networks can rapidly reverse the direction of information transfer. This provides a truly flexible routing mechanism, allowing information flow to be dynamically redirected based on context or task demands. This is particularly effective when the network operates in a transient oscillatory regime rather than in sustained, rigid oscillations. There's even a compelling hypothesis that the superficial layers of the cerebral cortex, the outermost, most complex layers, play a crucial role in functioning as such a delay-coupled recurrent oscillator network to manage this incredibly dynamic adaptive information flow.
So the brain doesn't just bind features, it can also flexibly route information just by subtly shifting the timing and phase of its internal rhythms. That's a level of dynamic control that's truly hard to wrap your head around. It sounds like a constantly reconfiguring, self-tuning network. Speaking of dynamics, let's talk about how the brain learns in this temporal symphony because it's wildly different from how artificial systems typically learn.
That is indeed a fundamental distinction, and it underpins much of the brain's unique adaptability. When we look at artificial intelligence systems, particularly the deep neural networks that have seen such success recently, their learning is primarily based on what we call supervised learning. In this paradigm, the weights of feed-forward connections are adjusted iteratively using algorithms like backpropagation. The network is given an input, say, an image of a cat. It produces an output, and then it compares that output to a desired correct result, the label cat. Any error is then meticulously propagated backward through the network to tweak the connection strengths, gradually minimizing that error over many, many iterations and colossal amounts of data. Critically, in most of these systems, temporal relations between events typically play a minor, if any, direct role in shaping these connections, beyond simply presenting data in batches.
So it's like a student who learns by repeatedly being shown the right answer and adjusting their internal rules until they get it right, with little emphasis on when they receive the information or the order in which specific events occurred. It's all about the final output accuracy.
Exactly.
Yep.
Now compare that to natural systems. The brain's learning mechanisms are exquisitely sensitive to temporal relations. This is a profound, foundational difference. Synaptic connections, the tiny junctions between neurons where information is passed, don't just strengthen when neurons are generally active, they strengthen specifically between neurons that are frequently activated together in precise temporal proximity. And conversely, they weaken when their activity is uncorrelated or asynchronous. This is the essence of Hebbian learning that we mentioned earlier. Neurons that fire together wire together. But the timing of that together is absolutely critical.
So it's all about the millisecond precision of who fired with whom and when. The exact choreography of neural activity is paramount.
Precisely. The molecular mechanisms for establishing associations in natural systems are incredibly sensitive to the temporal relations between activity patterns of interconnected nodes, often with millisecond precision. The exact timing of presynaptic inputs relative to postsynaptic neuron activity determines not only if a synaptic change occurs, but also its polarity, whether the connection strengthens or weakens, or even if it's depressed. This exquisite temporal sensitivity supports both the creation of those conjunction-specific neurons in feed-forward paths and the dynamic, flexible formation of neural assemblies we discussed. This allows the nervous system to learn the statistical regularities of the environment in a truly unsupervised manner, simply by observing and internalizing the patterns of co-occurrence and temporal sequencing in the world. It's constantly building an internal statistical model.
That means the brain is constantly figuring out how the world works, on its own, just by observing what happens when. It's like a relentless, curious scientist building theories from observations. But is it purely activity dependent? What about things like reward, attention, or emotions? Wait, do they play a role in what gets learned?
That's a crucial point that differentiates biological learning from many AI models. Learning in the brain isn't solely activity-dependent. It's cleverly gated and modulated by global modulatory systems. Think of key neurotransmitters like dopamine, acetylcholine, and norepinephrine. These systems are intimately related to states of reward, attention, motivation, and arousal. They essentially provide a now-print function, or a save-this signal.
A now print function, like a mental highlight reel or a selective memory button.
Exactly like that. When something behaviorally significant happens, you receive a reward, you're intensely focused on a task, or a situation is highly salient. These modulatory systems release these neurochemicals throughout vast areas of the brain. This acts as a powerful signal to selectively consolidate synaptic changes that occurred around that time, through a process often called synaptic tagging. This mechanism prevents dysfunctional modifications from happening due to random, spurious, or irrelevant activity. It ensures that only relevant or important connections, those tied to meaningful outcomes, are strengthened and solidified into enduring memories. It's a quality control mechanism for learning.
So it's not just neurons that fire together, wire together. It's neurons that fire together and are tagged as important or salient wire together permanently. That's a much more nuanced rule.
Very smart. Precisely. And this learning and consolidation process continues even when you're not actively learning or experiencing new things. Consider the phenomenon of memory consolidation, which largely happens during sleep. The brain spontaneously replays activity vectors from previous experiences, often with a unique oscillatory patterning and time compression, like a fast-forwarded highlight reel of your day or a musical piece played at a faster tempo. This replay, especially prominent in areas like the hippocampus, serves to solidify those memories, embedding them more deeply into the cortical network. This replay, along with the network's self-organizing nature, means that familiarity with stimuli actually improves classification over time, as the internal model of the world becomes more refined and the representations more robust.
So our brains are literally rerunning simulations of our experiences, both awake and asleep, to make them stick and refine our understanding of the world. That's an incredible level of self-optimization and continuous learning. It almost sounds like the brain is constantly building and refining an internal world model or simulation. And this leads us to how it processes information in what's often called a high-dimensional state space, drawing fascinating parallels to reservoir computing.
Indeed. This concept of the brain's recurrent architecture creating a high-dimensional state space is a crucial one, and it has striking parallels to emerging computational paradigms like reservoir computing or liquid-state machines in artificial intelligence research. In essence, it's a system where the complex, chaotic internal dynamics of the network itself are expertly exploited for computation, rather than relying on explicit programming or fixed, predefined pathways for every single piece of information.
So it's less about calculating a specific output and more about reacting or settling into a particular state within a rich, constantly churning internal environment, like a complex fluid whose ripples and eddies represent computations.
That's a powerful way to put it. A hallmark of natural recurrent networks like the cerebral cortex is their spontaneous resting state activity. This isn't just noise or the brain being idle. It's a very high-dimensional dynamic state that implicitly reflects all the stored knowledge or latent priors the network has accumulated about future contingencies in the world. It is, in essence, a continuously running internal model of the world, constantly simulating possibilities and relationships in the background, primed for input.
That's fascinating. So imagine your brain constantly running a very complex, high-resolution simulation of the world, even when you're just sitting there doing nothing in particular. It's always prepared for new input, with a baseline understanding of how things generally work.
Exactly. When sensory input then arrives, say the distinctive sound of a particular bird song or the smell of fresh coffee brewing, it acts as a perturbation, a disturbance to these ongoing resting dynamics. What happens next is a key computational strategy Singer highlights. If the input matches some of the stored priors or expectations, that rich internal model, the network state rapidly collapses from its high-dimensional complex resting state into a specific lower-dimensional and metastable substate. This substate represents the best match interpretation of that sensory evidence. It's not a search process, it's a settling process.
So it's like the brain has this vast, shimmering ocean of possibilities, and when new information arrives, that ocean doesn't just react randomly. If the input matches a familiar pattern, the entire ocean quickly focuses down to a specific, stable whirlpool representing a clear interpretation. It's not just recognition, it's understanding by settling into a stable state.
That's a wonderful extension of the analogy. And this collapse has significant computational benefits. These distinct substates, once formed, are well segregated in the high-dimensional state space, which greatly simplifies subsequent classification processes. Think about trying to find a specific item in a vast, cluttered room versus finding it in a meticulously organized library where everything has its place. Much easier, right? And because the transition follows stimulus-specific trajectories, meaning the way it settles is unique to the input, it allows for incredibly fast classification of inputs that strongly match the internal priors. The brain doesn't have to search. It just rapidly falls into the most probable, coherent interpretation based on its past experience.
That elegantly explains how we can process new information so quickly when it fits into what we already know, often almost instantaneously. What about information that comes in sequences, like a conversation, a musical melody, or a series of actions? How does that work within this fading memory framework?
This framework also elegantly explains the phenomenon of fading memory, which is critical for sequence processing. Stimulus-specific substates persist beyond the actual duration of the stimulus itself, not through a static memory buffer, but due to network reverberation. The activity literally echoes within the recurrent network for a short, precisely timed period. This persistence allows information from sequential stimuli to superimpose, while still remaining distinctly segregated in that high-dimensional space. This capacity for superimposition, without loss of identity, supports complex nonlinear operations. For example, it enables an XOR gate-like computation, where the output depends on the combination of inputs in a non-obvious way.
Just to clarify for our listeners, an XOR gate outputs true only if one of its two inputs is true, but not if both are true or both are false. So the brain's ability to handle this means it can process nuanced relationships like, I want coffee or tea, but not both, without needing separate hardwired circuits for every single possibility.
Precisely. The fading memory allows the brain to hold on to the first note of a melody just long enough to combine it with the second and third notes, even though the first one is no longer physically present as direct input. And crucially, information is encoded across many neurons in both their discharge rate, how often they fire, and their temporal correlation structure, how precisely they fire in relation to each other. It's a rich dual coding scheme, leveraging both the quantity and the timing of neural activity.
This all sounds incredibly dynamic and complex, which makes me wonder, how does the brain manage to control all these high-dimensional dynamics without spiraling into chaos or becoming totally overwhelmed? There must be powerful regulatory mechanisms at play.
You've hit on another critical aspect of the brain's design: dynamic control and efficiency mechanisms. For instance, top-down influences, like attention and expectancy, play an absolutely critical role. They don't just shift your focus, they could literally constrain and shape the dynamic space at lower processing levels, focusing the network's computational resources. If you're expecting something specific or paying close attention to a particular sensory stream, relevant stimuli evoke stronger and more precisely synchronized oscillatory responses. And preparatory cues can actually accelerate the formation of specific substates, effectively priming the network for incoming information, making recognition faster and more efficient.
So our focus or anticipation literally changes the underlying dynamics and efficiency of our brain, making it a more targeted and effective processor. It's not just a passive receiver of information, it's actively shaping its own processing.
Precisely. Additionally, the brain has robust intrinsic normalization processes. These sophisticated mechanisms are vital for preventing synaptic gain saturation and runaway dynamics, which would otherwise lead to uncontrolled excitation or, conversely, activity collapse. They preserve the relative weight distribution of converging inputs while remarkably keeping average discharge rates constant, even as the network adapts. It's a finely tuned, continuously recalibrating balancing act that ensures stability and efficiency. And there's compelling simulation support for all of this. Recent studies incorporating key biological elements like harmonic oscillators, self-connections, heterogeneous conduction delays, meaning signals arrive at slightly different times, and training with prior experience have shown significant boosts in hardware efficiency, learning speed, and noise tolerance compared to standard recurrent networks. This strongly supports the functional benefits of using the temporal dimension, just as the brain does.
So the science is actually starting to replicate some of these brain-like properties in artificial systems, showing that this temporal secret sauce is genuinely powerful and could lead to fundamentally new kinds of AI. It's not just theoretical, it's being proven in silicon.
It's an incredibly exciting frontier, illustrating just how much we can learn from the brain's unique and elegant approach to computation. It points to a potential roadmap for future AI that moves beyond current limitations.
Wow. Okay, let's take a breath and recap some of these truly mind-blowing insights. We've seen how the cerebral cortex, unlike conventional AI, is fundamentally defined by massive recurrence, that deep, looping, internal conversation complex, high-dimensional dynamics, and an exquisite millisecond-level sensitivity to time.
Absolutely. It masterfully uses oscillations and precise synchronization as a flexible, hardware-efficient code for relatedness, effectively solving the notorious binding problem by tagging information not just by what it is, but when it arrives in relation to other signals. And its learning is largely unsupervised and deeply temporal, beautifully guided by those sophisticated modulatory systems we talked about, which act as that now print function.
Right, the save this button. And its very resting state isn't idle. It's a vibrant, dynamic world model, an internal simulation enabling rapid computation through that ingenious process of state collapse when new sensory information arrives, quickly settling on the most probable interpretation.
Singer's ultimate argument is that the brain is a true hybrid masterpiece. It brilliantly combines the reliability of traditional feed-forward processing, those labeled line codes, where specific anatomical pathways carry specific information, with the immense computational power of a delay-coupled recurrent oscillator network. It uses both anatomical encoding and dynamic assembly codes, defined by precise synchronization to process information with remarkable efficiency, flexibility, and a profound capacity for real-time adaptation.
So what does this all mean for you, the learner? It means understanding that your brain isn't just a super fast calculator or a highly efficient digital computer designed to process fixed data. It's something far more profound. An analog, time-sensitive, self-organizing, and continuously learning system that encodes information in a rich, dynamic, multidimensional way. It's a powerful reminder of the profound sophistication of natural intelligence, the intelligence inside your own skull, capable of far more nuanced understanding than many current AI systems.
It truly changes your perspective on what intelligence can be, highlighting the elegance of dynamic, adaptive systems over purely static, pre-programmed ones.
Yeah.
It's beautiful, really.
And here's a provocative thought to leave you with. If the brain's incredible efficiency, adaptability, and capacity for deep understanding come from its unique embrace of the temporal dimension, massive recurrence, and high-dimensional dynamics, what might future AI look like when it fully masters these principles? When it moves beyond those clocked, purely feed-forward architectures to truly analog and self-organizing systems that learn and adapt continuously in a fluid temporal space? What new frontiers of intelligence might that unlock, and how might that fundamentally change our relationship with machines? We'll leave you to ponder that until our next deep dive.